Hi there. This is just a follow-up on the lesson which we had, and it's about the assignment. And we're going to do a bunch of calculations, and just to show how this is done. So we've got the situation where we need to have an amplifier that works as an active low-pass filter, so low frequencies pass through, and high frequencies are kind of blocked off. Yeah, so a low-pass filter, or what's it called? A low cutoff filter in the assignment. I'm just gonna quickly go on the computer whilst I'm talking to you to do the assignment. So first of all, let's do the op-amp graph, and this is what we are looking for. So we've got our op-amp here. We've got our inverting input. We've got our non-inverting input. The non-inverting input is put down to earth. So we're going to do this here. Then we've got our Rin, and we're going to go all the way through. We've got our output here, and we've got our RF, which is our feedback resistor, and that pretty much determines the gain. So we're going to join this all up here, and then we need to introduce a frequency element. Can you see it? Yeah, you can see it. I'm just checking with the camera. So we've got the output here, so that's the output. So this is minus V, that's our plus supply. So we've got V out at this point here, and we've got V in here. Okay, to introduce our frequency, so just to remember, capacitors, they hate DC as far as a signal going through them, but they love AC, so the higher the frequency, the lower the reactance. That's what it's called, reactance. Okay, so we're going to stick a capacitor all the way across here, and okay, so we're going to just put it in parallel with this resistor. Yeah. So what have you got with this capacitor now here? So we at low frequencies, like a DC, so for example, if I assume a gain of 2, I put this resistor as 1K, and I'm going to use this resistor as 2K. At DC levels, the resistance or reactance of this capacitor is going to be almost infinity. It's infinitely high, so there's nothing going through. So we've got a 2K resistor in parallel with a resistor that's got about I don't know, a million ohms or something. It's probably a little bit of leakage, but it makes it very, very high. Yeah? So the total resistance of this network is still going to be a little bit below 2K, even though this one is really, really high. It's just Ohm's law, the way Ohm's law works. Okay, so if I start having a frequency, the reactance will go down, so it'll go you know, a little bit lower than 2K, and then eventually it's going to hit a point where this becomes almost like 2K in reactance at a certain frequency. And so it goes down and down and down, and we hit our 3 dB point, and supposed to be out of gain. Okay, let's have a look at the 3 dB point. So if I draw a little graph here, and I've got my frequency here, so that's frequency, and I've got my signal voltage here, so that's V out. What I would find is I would sort of have a pretty much stable curve, you know, that's about gain of 2. So if I put 1 volt in here, that would be about 2 volts. So I put 1 volt in here. So I've got a gain of 2 with this feedback loop. Again, just quickly the formula for our op-amp. So V out is equal to minus let me just put this down, minus RF over Rin. So this is going to give me a ratio. Can I see this on the camera? Yeah, can just be seen. So it's going to give me a ratio, and so obviously always remember it's going to be a negative input. So a DC is going to be a minus signal which comes in, but if I put an AC signal in, it just swings up and down. It's just an inverted waveform which I get out on the other side. So as I increase my frequency, so at DC levels I actually would have sort of near enough minus 2 volts, but let's just assume for all intents and purposes it's a low AC level, so we've got like 1 Hertz. So the peak voltage would be about 2 volts here, yeah, even though it's inverted. And then eventually what we would find is we would find a voltage which would at a certain frequency sort of start dropping off, and then it would go down like that. At 0.707, 2 volts, let's put this down. So 3 dB point is at 0.707. So 0.707 times 2, that gives us 1.41. So at 1.41 volts, I would hit my 3 dB point. So I'm just going to drop a line here. So I assume, I mean, this is not precisely measured, but it's just sort of roughly. So I would hit my 3 dB point here. And then this would be, we call it FC, which is the cutoff frequency. And that's at my 3 dB point, right here, at this point here. Okay, and that's what we are looking for, really. So we are trying to configure the capacitor to give us a cutoff frequency. So what cutoff frequency can we go for? Again, in the assignment, you've got like a whole option. The gain should be somewhere between 2 and 5, I think. If I remember the assignment right, and the option might be somewhere between, I don't know, it's 20 kilohertz or something. I would have to look it up, but we'll do this later. Let's assume we've got a cutoff frequency of maybe for our telephone system. Our telephone system stops at 3.4 kilohertz, so that's our cutoff frequency. So that's what we are aiming for. Yeah? We want this to be 3.4 kilohertz. So that's our good old analog telephone system. So if you've got a microphone and we modulate it, we don't want any high frequencies to come through, we just want low frequencies to come through, so we cut them off at this point. Okay, how do we do this? Yeah, so first of all, we need to find out what gain we need to get to our cutoff frequency. Yeah? Again, we are wanting a gain of 2 for our average, or that's what we're looking at, you know, DC conditions. So we want this network to be equivalent to our, you know, having a gain or producing a gain which is equivalent to our cutoff frequency. So, for example, if we go along and we use our formula, so we look at normal gain is 2. So gain is 2. Our cutoff frequency will be at a gain at 1.41, really. That's what we're looking at as well. So so our gain in this instance, just in this scenario here, so if you use different values for your resistors, you need to use a calculation and go through them in a slightly different way. But for this scenario, we would have this total impedance, yeah, should be at 2 times, so that's our normal gain, and then 0.707, which is the factor for our 3 dB point, and the answer would be 1.41. So we need a gain of 1.41. Yeah, maybe a little bit confusing because the voltage is also 1.41, but it's just the using the figures we're using. So if we change the figures, obviously the voltage would be higher, and so on would be a multiple of that. Okay, so hopefully you're still with me. So we are looking for a reactance of 1.41. Okay, let's have a look at the formula. First of all, the formula for 2 resistors in parallel. 2 resistors in parallel, RT is equal to R1 times R2 divided by R1 plus R2. So that's RT. Now, if we look at this one here, we don't really have a resistance here. We've got a reactance because it changes its frequency. Yeah. We know the frequency we want to cut off, which is 3.4 kilohertz. We don't know what capacitance to use, and we don't know really what reactance we are looking for in this context here. So right, let's have a look. See how we can change the formula. So we put down RT. So that would be XC times R2. Minus XC plus R2. Yeah? So we would have our formula slightly changed. Instead of R, we are using X for reactance. X maybe because we don't know where this is leading to. Okay. How do I find out XC? It's the next question. And XC, the formula for that is 1 over 2 pi FC. So again, we know F, which is 3.4 kilohertz. We don't know C, and to be fair, we don't know XC at this moment either. We don't know what XC has got to be. So we need to figure out, first of all, before we can complete this formula, we can find out what capacitor we have, what we need to do here. And we have to transpose our formulas to calculate them for XC. We need to know what XC is. So we know we've got 1K here, we've got 2K there. So we know R is 2K, R2 is 2K. But XC, we haven't got a clue. Okay, so how do we transpose our formula? Right, so I'm just going to go through the stage, because we need to find out what XC is, you know, and we need to come up with the formula for XT. So first of all, we need to get all our XCs on one side. Yeah, so we need to get XC on one side. So I'm going to change the formula. I'm going to multiply this side with XC plus R2. Yeah, so we do this to both sides. So we get RT times XC plus R1, sorry, R2 in brackets, and then that would give me, that would isolate the other expression, so we would have XC plus times R2. So that's by just transposing the formula. What I've done is I've multiplied both sides with XC plus R2. So if I multiply this side, so with XC plus R2, and the other side as well, so in this side this would just cancel out, and all I'm left with is this expression here. Okay, I need to transpose a little bit further, because still XC is on both sides. Yeah. So what can we do? First of all, we can start factorizing this expression here. So we've got RT times XC plus RT times R2. Yeah. And that's equal, still got the same expression here, XC times R2. Okay, I need to get both XCs onto one side. So what do? So I just subtract this side, or subtract RT times XC from both sides. Let's do that. So we've got RT times R2, and then we've got right, RT right, let me get this right. So we've got XC times R2, put this in brackets, minus RT times XC. Hope I got this right. Okay. And there should be a minus sign between here. Okay, so I can start factorizing this. So let's go one expression further. So I've got RT, still the same thing, times R2. And then again, this expression is XC times R2 minus RT times XC. So I'm going to factorize it, and I end up with XC times R2 minus RT. So okay, that's factorized now. So I've isolated XC, so I can just move this expression to the other side. So I divide by R2 minus RT. So I do this, just wait for, so it's RT times R2 divided by R2 minus RT, and that gives me XC. Yeah. So I can now stick in my figures and come up with a value for XC. And bearing in mind RT should be 1.41K. So it's not 2K, but 1.41K. That's what we calculated. So that's the gain which we need. and that would give us the 0.707 point. Okay, let's do this. Stick the figures in. So we've got RT is 1.41 K times R2, which is 2K, divided by R2, which is 2K, minus RT, which is 1.41 K, and that should give me the value for XC, and we can figure it out or try and work it out whether it actually works. Okay, so let's do the calculation. I have to use my calculator for a moment here on the laptops. So the first expression is 1.41 times 2. So that should be fairly easy. It's 2.82. Let me see, can you still see this? Yeah, I'm just checking with the camera. So it's 2.82 K. And then we've got 2K minus 1.41 K. That should be 0. Am I getting it right? 59 K. Yeah. And that should be XC. Maybe okay with subtraction and doubling stuff, but not very good with division. So let's try it out. So divide this expression on the calculator by 0.59, see what it comes up with. And we got 4.77 K. So XC is equal to 4.778 K. Yeah. So that's the result I've got. Let me just write this down a bit more clearly. So it's 4.78 K. That's what XC should be to get our desired result of 0.707. The cutoff point of 0.707. Okay. Does it sound okay? Kind of. Yeah. So if we get this value, so if you've got a 2K and a 2K resistor, we would have 1K here, that would be unity gain. If we've got a 2K and a 4K, we've got something like a total value of 1.5K. So it's about okay. Yeah, it sort of works out about there. So we know the value for XC now. So we know that XC is, but still we don't know the frequency. We know the frequency as well. We don't know the capacitance to use for this circuit. Okay, let's transpose this formula, because the only value we don't know for this formula here is C. So C is equal to 1 over 2, let me just put the bar here, 1 over 2 pi, the frequency is 3.4 kilohertz, so we put on 3.4 kilohertz times 4.78 K. 4.78 K. Okay, so let's do this. Add all this together, so we've got 2 times pi is 3.14, so it's 6.28, 6.28, I'm just doing it on the calculator on the computer, times 3,400. And then times 4,700. That's right, yeah, 4,780. 4780. Okay, so that gives us a very big number. Okay, I need to go into scientific mode now. Don't know whether I can do this on this calculator here without losing the number. No, I've lost the number. Anyway, let's do it again. So we've got 6.28, 6.28. It's only a fraction of, obviously a lot more figures to get exactly pi, but it'll do for us. Times 3,400 times 4,780. Yeah, so this gives us, I have to look at the figures, so it's It's 102 million and something else. So we have to. Okay, we take 1 over, and we get an 9.97. That's the result. So C is equal to 9.79 times 10 to the power of -9. So -6 would be micro, -9 is nano. So C, we could say, is near enough 10 nanofarad. Yeah, this is correct. 10 micro, nano, pico. Okay, 10 nanofarad. So we take a 10 nanofarad capacitor, and that's what we have calculated here. I don't know whether you can see this. Just make sure. 10 nanofarad capacitor, which we would have to stick in here. Okay, so my circuit, according to my calculations, should be just going to go through the paperwork. So we should have a 1K in here, we should have a 2K capacitor in there, a 10 nanofarad capacitor there, and then the cutoff point here would be at 3.4 kilohertz according to this circuit, and that would just be a telephone circuit. Telephone circuit goes from 300 hertz to 3.4 kilohertz for analog voice. And that would give us our 3 dB point, yeah, so just call it the 3 dB point, which is at 1.41 times, in this instance, at 1.41 volts, or a gain of 1.41 as well, because the way we've chosen our figures, or it would be 0.707 our maximum voltage, you know, our normal gain voltage. So if you have unity gain, it would be 1 volt or whatever, and then 0.707 at this point. If we've got a gain of 3, would be a lot higher, and so on. Okay, I hope this makes sense. The formulas to remember is this one here. I don't know whether you can see this. I've just circled it. So that's a key formula to do your calculation. And that should give you the value for XC. Obviously the other formula for XC is this one here, yeah. Which gives you, you know, the frequency where you want your cutoff to be. You know your, XC. You just transpose the formula slightly. So C, let me just write down the formula for C. C is equal to 1 over 2 pi f XC, the reactance. Yeah, so that would be the formula you'll be using. So those two formulas, they are key. Can you see them? Yeah, you can see that one for you know your frequency, you know your reactance after you've done the formula for 2 resistors in parallel, and then you can find out what C is. You can stick it into the circuit, which is up here, and once you've stuck it into the circuit, you can then put it into multisims and try and find out whether it actually works the way it should work. If we look at XC, we got a value for XC to get what we want of about 4.78K. We've got 2K for our gain at DC levels, and we know roughly that it's gonna work out. Yeah. So the waveform is probably, or the gain is probably gonna go a little bit like that. Yeah, and then go down. So because that value is fairly close to the to this resistor here, so it's going to drag the gain down quite significantly to start off with. Okay, I hope this little demo helps, and I hope it is going to get you on your way to successfully doing your assignment.